The semi-refrigerated ship makes use of this phenomenon. Here the cargo is semi-pressurized and thus can be allowed to reach a higher temperature than in a fully refrigerated and non-pressurized vessel. But now back to boiling point itself. Here are the boiling points of the more common cargoes given at the standard pressure of 1 bar. It's not always sufficient to think of the cargo in pure liquid or gas form. It must be remembered that during vaporization, vapor will carry varying degrees of moisture content. Excessive vaporization causes expansion and venting and increases the need for reliquefaction. Under certain conditions of temperature and pressure, a state of equilibrium will be reached, and such vapor will cease to vaporize to its full gaseous state. To carry our cargo successfully, we must reduce vaporization to a minimum, and thus the relationship between pressure and temperature is a critical factor. Just to recap, it's the combination of these factors which maintains the equilibrium of the cargo. The three factors are: 1, the gas itself; 2, the pressure at which it's carried. Increased pressure reduces vaporization. And 3, the temperature at which it's carried. Reduced temperature reduces vaporization. The suitability of a ship to carry a particular cargo will depend, of course, upon the refrigeration and pressurization plant available. They must be able to achieve the required performance levels. To assess in broad terms whether a ship is capable of carrying a particular cargo is a relatively simple matter, with the aid of a vapor temperature and pressure chart. Knowing the maximum carriage pressure and minimum carriage temperature for the ship, select the point at which these two coordinates meet. Gases whose curves lie to the right and below the point can probably be carried. Those whose curves lie to the left and above the point cannot be carried. Just to clarify the point, here's another example. In this case, the ship's maximum operation is minus 30 degrees centigrade at a pressure of 2.8 bars. Inspection of the graph shows that she could probably carry butane, butadiene, vinyl chloride, ammonia, propane and propylene. She could not carry ethane, ethylene and methane. There are, of course, other physical properties that must be considered when handling gas cargoes. For instance, what about relative density and specific gravity? Well, we need to consider them both. Firstly, relative density, or as it's sometimes known, vapor density. To refresh your memory, relative density is the relationship between a weight of a gas when in a vapor state compared with the weight of an equal volume of air at the same temperature. If it is lighter and its density is less than 1, it rises. If it is heavier, with a density greater than 1, it falls. This property is particularly important when we consider whether a dangerous gas concentration could develop. For instance, when venting, if the relative density of the gas is greater than 1, it will tend to sink to deck level. This is why the vent pipes are so high, to allow the vapor to be blown away before it reaches deck level. Similarly, it's of importance to know how it would behave, say, if there were a leak in a compartment such as the reliquefaction room. Would it occupy upper or lower spaces? Here are the relative densities of some of the gases at the reference temperature of plus 20 degrees centigrade. It should be remembered that as gases are heated, they become lighter and heavier if cooled. For instance, methane, or natural gas, is heavier than air at its boiling point of minus 162 degrees centigrade, whereas at plus 20 degrees centigrade it is lighter than air. This means that if methane were vented to the atmosphere at its boiling point temperature of minus 162 degrees centigrade, it would sink. Then, upon exposure to atmosphere, it would heat up and rise as its relative density decreases. Specific gravity is similar in some respects to relative density. It concerns the mass relationship between a solid or liquid compared with water. In other words, specific gravity is the ratio of the weight of gas in its liquid form relative to the weight of an equal volume of water at the same temperature. Providing the liquid is insoluble in water, then a liquid with a specific gravity greater than 1 would sink, and if less than 1, it would float. This, of course, is only true if the gas remains in its liquid state. In the event of any spillage, vaporization quickly takes place, and so the relative density and not the specific gravity of the gas becomes our major concern. Our interest in the specific gravity of the cargo lies in its use in cargo capacity and stability calculations, as its weight is proportional to its specific gravity. Here are some of the specific gravities of the more common cargoes. Remember, these values vary with change in temperature. Just to recap, I'll briefly remind you of the points we've discussed. Critical temperature. This is the temperature at which gases will not liquefy under pressurization alone. Critical pressure. This is the pressure below which liquefaction cannot occur. Here we discussed latent heat. You'll remember this is the hidden heat that is absorbed during vaporization or similarly lost during reliquefaction. The boiling point of a liquid is of course the temperature at which vaporization takes place. Vapor pressure and temperature relationship. We discussed here the importance of maintaining equilibrium and evaluating the suitability of our vessel to carry different gases using the chart. Finally, we discussed relative density and specific gravity and their relevance